This meme today happens to pertain to the lesson that we're going to be learning today, all about antiderivatives. So now that you guys are somewhat good at taking the derivatives going forward, we're going to be looking at, if you're given a derivative, finding the original function to that, so working backwards. But I will say that this lesson is just a taste of what we're going to be doing in Chapter 5, more so with integrals. So the expectation is really, just learning your trig derivatives and knowing what the antiderivatives of those would be. So your 6 trig derivatives, as well as if you recognize any formulas like natural log, or if you recognize that's an inverse trig function, working backwards to find what that would be. But this is just all formula sense. You don't have to know sort of some tricks yet on finding the antiderivatives. It's just if you're unable to find the antiderivative, see if you can manipulate that so that you're able to do maybe what we call the reverse power rule today. So here's your warm-up for the day. It says, given the derivative below, see if you can find the original function. Now, one nice thing about any of these today is if you think you've found the original function, you can always take the derivative of that to see if it matches up. So take a moment, pause the video, and see if you can come up with the answer to all 3 of these questions. Good luck. So in the first one, with derivatives, and specifically with polynomials, it always decreases by power. So working backwards and finding the antiderivative, it would increase as a power. So we know it's going to be some x cubed. But notice if I take the derivative of x cubed, that ends up being 3x squared, and I don't see that 3 in front of x squared. And so it's sort of like making up for that 3 that would have been there by multiplying it by 1/3 in front. And so our antiderivative ends up being 1/3 x cubed there. For sine, working backwards, well, the derivative of sine is cosine, and so the antiderivative of sine, so our original function here we'd notate as lowercase f, would be negative cosine, right? Because the derivative of negative cosine would be then positive sine, so that works out. And then remember, any e to the x's end up being d to the x. You should recognize that formula at the tail end. So the original function here ends up just being 2e to the x plus 1 over x. The antiderivative of that is natural log of x. Now, we are true somewhat with all these, because in any situation, these could be any variations up or down. These could be translated up a few units, down a few units. We don't know where these are on the graph. And so what we need to do is when we take antiderivatives today, you need to add a plus c at the tail end of every problem today, especially when you're working out the antiderivative, because we need to represent any vertical transformations, any constant, because essentially the derivative of constant is 0, and so we'll just put a plus c in place of that. It is important that we remember that each part, and so get a habit of it, because if you don't, puppies will be hurt, and that's my only way to kind of get through students and remembering to remember plus c every time. So just think about this plus c, this puppy when you write plus c, or if you forget to write plus c, because if you forget, a puppy may be hurt in the future, and you don't want that sad puppy to be hurt there. So point is, remember plus c for today. So here's a theorem that says if capital F is the antiderivative of lowercase f, and this is just the notation we use, so if I give you like the function's given as f of x, then working backwards, the antiderivative would be notated as capital F. But working forward, you use this f prime to represent derivatives. So if I give you something that's f prime and you're working backwards, then it makes sense that I'd notate it as just capital or lowercase f there. And then if I did one more time, then I'd be notating that as capital F if I wanted to depict the antiderivative again. Just some little notational things, but then again, that's how that plus c is introduced, and there's a picture of why that's true, because you don't just come up with the answer of 1/3 x cubed. There's any variations of that because the derivatives of each of those constants end up being 0. So the reverse power rule. Well, if you remember the power rule itself, it's for any x to the n where n is some integer. The power rule itself is that we brought that down in front, and the derivative ended up being n times x to the n minus 1 power, the 1 less power. So what the reverse power rule is if I'm taking the antiderivative of something like this, the antiderivative then would be, well, it makes sense that we would be adding a power, because working backwards we add a power to whatever that might be. And really it wouldn't be n in front, we'd have to divide by whatever that new power is. So this is the formula for reverse power rule, which is kind of the main formulas we're going to be working with today, besides memorizing your other derivative formulas. But this is our reverse power rule formula that we use. So this is just a page that summarizes sort of all the formulas and rules you got to remember for today. The first one obviously is just that power rule with the plus c involved. The other few are just saying that you can distribute antiderivatives separately, just like with derivatives. There's our reverse power rule here, knowing that the antiderivative 1 over x is natural log of x. And usually when we work backwards, we do encourage you to put absolute values of x around there because the domain of natural log is all positive numbers. The antiderivative of cosine is sine. So know your trig functions. And also recognize if you see a formula that looks like one of these, that chances are it's probably a inverse trig function of some sort. So this is just a summary page of really everything you should know before we get to some of these problems. All right, so let's take a look at it. It says find all functions g such that the derivative is this. So we're trying to work backwards in this case, and it says all functions. The reason why it says all functions is just that plus c makes an account of all variations of that up or down. So the first term wouldn't be too bad, but when we get to this term, we don't know a reverse quotient rule yet. And so the expectation is to try to manipulate that term somehow. And if you notice, it's over a monomial, one term on the bottom, x. And since it's over x, what I can do is sort of separate those two terms on top, basically doing the reverse of like common denominator work, right? So I'm going to first rewrite this derivative before I find the original function. And specifically, I'm going to write that function as 2x to the fifth over x minus the square root of x over x, just splitting up that term separately. And if I do properties of exponents, notice that the first case, 2x to the fifth over x, just reduces one of those x's, so it becomes 2x to the fourth. And then if I think of that as x to the 1/2 over x to the first, if you do properties of exponents there, I get x to the negative 1/2, so let's just keep it as negative x to the negative 1/2. And now working backwards, my antiderivative would be lowercase g here, because that would be the original function we're finding. Antiderivative of sine is negative cosine, and coefficients stay, so the first term would be negative 4 cosine of x. Let's do reverse power rule here. So if I add a power of 1 to 4, it becomes a power of 5. Coefficients stay, and don't forget you have to divide by that new power. So 2/5 x to the fifth ends up being the middle term there. And then reverse power rule here, I would add a power of 1, which is thinking about that as 2/2 there. So if I add 2/2 to that negative 1/2, you get 1/2 itself. So my new power ends up being 1/2, but then don't forget you're dividing by 1/2, which if you divide by 1/2, keep, change, flip becomes multiplying by 2. And then again, don't forget, get a habit, plus c at the very tail end. And like I said before, if any of these today you're working out and you're unsure, well, take the derivative of that and see if it matches up with the original function. Let's take a look at another one here. This is a case where we might have an initial condition, and these are called initial condition problems or initial value problems. But that last little part there after we find the derivative, that allows us to find c itself. Find that actual constant that it goes through if you're given a point that the original function goes through. So let's first kind of rewrite this a little bit. It says the derivative is given as e to the x plus, that negative 1 power really means over that to the positive 1. So I can first kind of rewrite it as 20 over 1 plus x squared there. And you might not recognize the antiderivative of that yet, but if I manipulate it slightly again and call it 20 times 1 over 1 plus x squared, I think a lot of you might recognize what that antiderivative is going to be. So the antiderivative, which I notate as lowercase f, while the antiderivative of e is just e to the x, coefficients stay, so it's going to be plus 20, and then the antiderivative of this, some of you recognized, yep, that's tangent inverse of x. That's our formula for tangent inverse of x. So then it'd be 20 tangent inverse of x, and then don't forget plus c, and then that would be our final answer. So to find the c value here, using that initial condition, the initial condition said that if I sub in 0, my output's -2, it looks like. And so that means if I sub in 0 for x, right, that my f of x is -2. So if I replace f of x with -2 and sub in 0 wherever I see an x, that allows me to find that coefficient c. Don't always assume that if I sub in 0 that is my c, because when you sub it into trig functions, or in this case e functions, right, e to the 0 is not 0, it ends up being 1. So that's not necessarily your c value itself. You actually have to plug it into and really solve for c to figure out what it is. So if I simplify, e to the 0 is 1, tangent inverse of 0 is 0, so it becomes this. So if I subtract 1 over, it looks like c is -3. And so my final answer, if I go back and plug that in, it would be -3 there as my overall answer. So e to the x plus 20 tangent inverse of x, and then -3 is my constant there. Working backwards, let's take a look at one more here. And this is one where I'm giving you the second derivative now. So we have to work backwards twice to find the original function. And notice there's conditions here for just the original function. And so we might have a c and possibly even a d value that we might work with. So notice that our second derivative is just a polynomial. So working backwards, we're just going to have to do the reverse power rule. And so let's work backwards once, which would be the first derivative. So if I focus on that first term, 12x squared, well, if I add a power of 1, that becomes a power of 3. And if I divide by that new power and simplify that coefficient, it looks like I end up getting 4x cubed for that antiderivative, plus the antiderivative of 6x. If you think of that as 6x to the first, I'd add a power of 2, but don't forget you're dividing by 2 for reverse power rule. So that becomes 3x squared. And then the antiderivative of any coefficient is always that number x. And then don't forget plus c. Now with any of these initial value problems, if you have a couple conditions, you always want to check to see if we have a derivative condition here. And notice both of these are in terms of the original function. So if we did have a derivative condition, we could actually sub that right away and find c before we work backwards again. But since we don't have that derivative condition, we just have to go ahead and work backwards again. And so the antiderivative of 4x cubed, if I add a power of 1, is to the 4. Dividing by 4 gives you 1, so I believe that is x to the 4th. Antiderivative of 3x squared would be x cubed. Antiderivative of -4x, if I add a power of 1, that's a power of 2, and dividing by 2 gives me -2x squared. And then the antiderivative of c, any constant, I guess would just be cx. And then I have like a new coefficient, we'll call it d. But now let's use that information above to figure out what c and d are in our equation here. If we start with f of 0 equals 4, that condition, that means if I sub in 0 for x, the output's 4. So that means 4 equals 0 plus 0 minus 0 plus 0 plus d. I subbed in 0 for all the x's there. And so right away, by doing that, that does tell you that d is 4. So I can plug that in right now for d, and d is positive 4. So now if I use that second condition, that's going to let me find c. So that means that if I sub in 1 for x, right, that's your x value, that the output f of x is 1. So if I sub in 1 for f of x and 1 for x, wherever I see an x, 2 times 1 squared plus c times 1 and then plus 4, then this equation here, if I try to isolate c, would give me that c value. And so if I, looks like these are going to cancel each other. 1 plus 1 minus 2 is gone. And looks like if I subtract 4 over, it looks like I'll get c is -3. And so I go back into my original problem and erase that coefficient of 3 and write it as -3 in front. And so this would be my final answer in the end. So see if you can try both of these on your own. They're not too difficult to work out. Notice the first one, both of these, by the way, have the second derivative given, and you're all finding the original function. And so you have to work backwards twice with both. Notice the first one has something in regards to the first function and something in regards to the derivative. So I believe once you do it once, that allows you to find that plus c, then work backwards to find out a new c in that last condition. But notice the last one only has, in terms of one function, so this is the one where you have to work backwards twice, and you might have a cx and then plus a d again like we had before, but then go ahead and find those c's and d's using those last two conditions there. So good luck, pause the video, but try your best on these, and we'll go over the answer in a few minutes. All right, let's check the first one here. So given the second derivative, if I work backwards using reverse power rule, the first derivative, well, the antiderivative of 4 would be 4x. The antiderivative of negative 6x would be negative 3x squared by reverse power rule. And then the antiderivative here, if I added a power of 1, would be 4. Dividing by 4, I think, gives me negative 10x to the fourth. But remember, we have a plus c. And now that I have a derivative condition, I can plug that in. 0 for x and 1 for the output there, and I should be able to find c before working backwards again. So if I sub in 0 everywhere there's an x, and my output's 1, that means c is 1 itself. So I can plug that in, and now I actually know what the c value is 1, and so now I can work backwards from there. So then the original function f by reverse power rule would be 2x squared minus x cubed. If I add a power of 1 here, that becomes a power of 5. So dividing by 5 gives you negative 2x to the fifth. And then the antiderivative of 1 is x. And then I have a new c to find in that second stage. That's when I use this condition, that if I sub in 0 for x, that the output's 2. So then f of x is 2. And if I sub in 0 wherever I see an x, looks like since this is a polynomial, that ends up being my c, so c equals 2 in this case. So if I go back and plug that in, c is positive 2. This would be my final answer for my original function. And hopefully you got the same. If we look at the second one here, both of these conditions are for the original function, so we're going to have to work backwards twice without finding c. So if I work backwards once, doing antiderivative work, the antiderivative of 2e to the x is 2e to the x. The antiderivative of sine is negative cosine, so it ends up being negative 3 cosine of x, and then we have a plus c. I always check to see if there's a derivative condition, which we don't have, and so now I'm jumping back to finding the original function, working backwards again. The antiderivative of 2e to the x is still 2e to the x. Now the antiderivative of negative cosine is going to be negative sine of x, and then the antiderivative of c is just cx, and then I guess we have a plus d at the tail end. Now it doesn't matter where you start on conditions. I always like to start when we're subbing in 0 because that might find something right away. So if I take that first condition and I replace f of x with 0, and wherever I see an x with 0, notice that the c value is gone when I sub a 0 in. And my d value, if I kind of simplify, I get 0 equals 2, sine of 0 is 0, so I get 2 plus d, so that means d is negative 2. And so if I go back and replace d with what we found, it's negative 2. Now I can use that last condition to figure out what my c value is. So if I use that last condition, that if I sub in pi now, my output's 0. So the output's 0, and if I sub in pi for x, plus c times pi minus 2. If I try to solve for c by itself, let's just keep our answers exact. I know that sine of pi is 0, so that term doesn't have any effect. But to solve for c, to isolate it, I would have to subtract the 2e to the pi, add the 2, and then notice I'd have to divide by pi to each side. And so it looks nasty, but c is going to given as negative 2e to the pi plus 2 all over pi. And I guess we just have to take it as it is. So my final answer, if I write it out, my original function is 2e to the x minus 3 sine of x, and then plus, there's my coefficient in front of my x, and then minus 2 was my d value. So then that is my final answer there. So a little bit harder of one, especially when you're finding c, but it's just a lot of algebra work there. Before we get to the last part of the lesson, which is really just tying the same stuff we've done to vertical motion, that kind of stuff, particle motion, so velocity and acceleration functions, I wanted to see if you could work this one out on your own. And this is a puzzler. This is one of the more challenging antiderivatives we come across. But I'll give you a hint. If you try to split up that term somehow, you might be able to recognize maybe a formula per se, or but try your best on this. If you get stuck, we're going to go over this in a few seconds, but this is one of the more challenging ones. You won't be expected to do something like this on assessment necessarily, but I wanted to throw a harder one at you today. So good luck. So I don't know if any of you saw this, but one thing you can do is split up these terms separately. In fact, if I rewrite this derivative as, on top, splitting that 2 as 1 plus 1, notice I kind of have the same expression in the numerator and the denominator, part of it at least. And so what I can treat that denominator as is treat that as sort of, I know it's a 2-term, but treat that as 1 term in parentheses and try to split up this separately. And so if I split up the numerator, I can write that as 1 over 1 plus x squared plus 1 plus x squared over 1 plus x squared. Basically reverse common denominator work. And notice when I do that, you recognize right away that, well, this reduces to 1, and this first term ends up being a formula. In fact, that's the antiderivative of tangent inverse of x, or that's the derivative of tangent inverse of x. And then since I have plus 1 on the outside, the antiderivative of 1 is x, and then don't forget, it's an antiderivative we're dealing with, so we have to remember that plus c in the situation. So a little bit of a challenging one. Hopefully some of you got to that a little bit. So the last part of the lesson, a couple quick things. Particle motion. So it's just basically doing the same thing, but now I'm giving you like the velocity function. So if you're working backwards, we do notate that as position. Remember, working forwards would be acceleration. So if I give you acceleration, you might have to work backwards twice to find the position function. But here it's just find the position of the particle. And so I want the relative formula for what the position looks like. So if I take the antiderivative of this first term, that ends up being t squared. And notice that's, again, tangent inverse. And so it ends up being tangent inverse of x, and then don't forget plus c. And then now I use that condition to find c. So if I sub in 0 for x, my output's 1. So if I sub in 0 for t in this case, that the answer is 1. And the tangent inverse of 0 is also 0, so that means c is 0 itself. Or sorry, c is 1 itself. And so my final answer would be this. And I know I probably should have had it in terms of t there, but there we go. That would be my position function. So here's a case where I give you acceleration, and then you need to work backwards twice to find position. But notice there's a couple of conditions that allows me to find c in the first step. So there's your velocity condition, and then here's your position condition to find c on the second step. So you don't have to do that like cx plus d step. Both of these conditions I can kind of work through as I go. But if I'm given acceleration, the antiderivative of acceleration would be velocity, and the antiderivative of that would be 3t squared plus 4t plus c. And then this is where I'm going to use that first condition, that if I sub in 0, it's -6. And since this is a polynomial, that ends up being my c value, so -6. And then working backwards again would be giving me position. So finding the antiderivative velocity would be t cubed plus 2t squared minus 6t, and then plus a new c. And then this is where we use that last condition to find our new c. And since, again, it's a polynomial, if you sub in 0, that will be your c value there. And so if I plug that back in, my final answer would be this. So here's your homework. Practice as best you can on those. There is a Antiderivingo game if you wanted to check out on your own. It's located in the modules. It's just a little game. You can kind of puzzle through some questions, get some extra practice on some antiderivatives. But that really concludes all the sections in our next assessment. So tomorrow we're going to review, and the next day we'll be taking that assessment online. So it'll be a quiz that covers sections 4.5 through 4.9. Make sure you're keeping up on the homework, and make sure you're taking advantage of that homework help in case you have any questions outside of class. Enjoy the rest of your day.